Good afternoon, everyone, and welcome to our talk. We hope that this slot will not get you too drowsy. Everybody had something to drink after lunch. You feel a bit more awake. And we'll try to make this, if not entertaining, at least plausible in a sense. Before we begin, there's a lengthy disclaimer that you're all required to read and sign off on. That's it. No. In all seriousness, I used to work for Intel, not any longer, which is why you can see me crossed out at the bottom, and why I can make this joke and say you don't really have to read this anymore.
But please read, because I still work for a Fortune 50 company.
Someone has to. My name is Guy, and this is Ezra. We're both co-organizers of the Tel Aviv B-Sides, which happens around June, and you're all very welcome to join us in sunny Tel Aviv. It's a pretty awesome B-Side, just like here. And we go and often talk about topics that cross both of our domains of expertise, with this talk being one of them. We do have some experience, and we travel the world to some of the finest conferences out there. We both believe that BSidesLV is the one of our most lovable, best conferences we love to attend, love to speak at, because this is the one that's most homey, most approachable, most community-driven. And this is something we wanted to point out. Before we begin, a bit of a history about how we came about to this topic and about the talk that we're going to do today.
Because it's funny, you remember we were maybe a year ago.
About a year ago, yeah.
And we had a couple of days in San Francisco.
And we were driving our car, our rental car.
And we're like, wow, this year we have some very good content. And we were like, we were talking about machine learning, and we have some amazing experiences. And it was like, fuck, what are we going to do next year?
So last year we did a talk here in this very same room about machine learning and how you would hack machine learning. And we were trying to think about, okay, this is a good topic. This is something interesting, which we both like. What can we do with it next? What's the next step? And that next step and that conversation led us here today, which is how can we actually use machine learning to help us in our everyday life, in our jobs, of actually finding and exploiting issues in various systems that we explore.
So let me start with our problem and how it is related to our last year talk. Last year, our objective was to hack the hell out of machine learning. And when I'm talking about that, I'm not talking only about the algorithmical part on the adversarial networks. I'm also talking about finding vulnerabilities in the different frameworks that exist for different machine learning purposes. So we did what we researchers love to do the most, and it's basically run a fuzzer. And this fuzzer started to generate thousands of crashes to analyze. And you can imagine that this is a good problem to have. Having a lot of crashes is good. But having a lot of crashes brings us a small issue. Not all of those crashes are exploitable. And automation can do some good work, but we may miss some things. I mean, using heuristic approaches to find which of our crashes with GDB are exploitable works, but we may miss a lot of interesting stuff. On the other side, doing it manually is extremely expensive. Me as a researcher and my team of researchers can only go through a small amount of crashes. Like imagine for every single crash we need to reproduce, we need to open our GDB debugger, and we need to take a look of the entire flow to know if it was exploitable or not. And well, this doesn't scale at all. And when we saw that it doesn't scale, we thought that our work would be mostly about building the model, because we had the crashes, and we thought, well, we are going to be working a lot on building this model. And then we saw that the real problem was starting to gather the data. Because imagine now that we have thousands of crashes, but we don't even know what's their status. We don't know if they're good crashes, bad crashes, the same crashes. We don't know anything about them. So gather the data became a big problem. And then we struck the real problem, which is gathering good data. Because there's a big difference between data and good data. Like if I have 10,000 crashes that all of them are going through the exact same path, it's the same as having a single crash. It's not relevant for me at all. So this was the problem. Finding what is the good data. Finding how we can sift through different crashes and try to understand how we can leverage them. So our problem statement became something like this. Can we, as researchers, generate a machine learning model that can help us with the triage crashes and help us find exploitable ones? And again, remember that our problem burned with thousands of AFL crashes.
So to summarize that and kind of like put the focus, put the spotlight on our problem is, we have a team of researchers. In this case, my team had about 5 researchers. 5 researchers can go through, I don't know, maybe 10 to 20 crashes a day in a very good day. We have 10,000 crashes. This does not scale. This is not the solution. And more than that, in order to look at those 10,000 crashes, usually you'll see a lot of crashes that are duplicates of each other. And that means you're wasting a lot of time in finding out that they are duplicates of each other. So the big question is, can we use machines to help us sort out the exploitable paths or the exploitable crashes that we actually want to look at and invest the time and resources that we have into where we can actually drive impact? So that was the big research question. And the way we try to tackle it is to see if we can build a machine learning model that would outperform, would actually be better than the best known alternative, which is an open source project, which is called exploitable. Because the name is so confusing, I've underlined it, and every time that I will refer the open source project, and it says exploitable with an underline, I mean the open source project. And I say exploitable another way means it's just exploitable. So this talk will not show you how to exploit the next 0 day. This talk will not be releasing new tools and methods in order to exploit something new that you haven't seen before. But what we are going to show you in this talk is how to utilize, how to build such machine learning models and see where they can help you and where they cannot, and try to differentiate between the two cases and walk you through the research path that led us from an idea to something that actually works, and the hiccups that we found along the way. We do want to say beforehand, we really can't trust our results. And we'll explain in the end why we can't trust the results. But you should always keep a very specific eye on the details, because the details are what really matters. So we'll be happy to expand after the talk if someone has specific questions or issues. So I'm not going to do this like 101 into machine learning, what it is, but I'm going to give you like a very high-level overview of how machine learning actually works. So machine learning has a couple of different paths when you're building a machine learning model or running a machine learning model. The first step is that you have to give it the data. And in order to give it the data, you have to collect the data from whatever sources you get your data from. And then you have to extract from that data the pieces of information that you want your machine learning model to look at. For example, if you're looking at a log file is a large piece of data, maybe, I don't know, 1 million log lines. But the machine learning is not really reading 1 million log lines. You have to extract from each line the specific items that you want the machine learning model to look at. The timestamp, the host name, the alert level, the stuff that you want it to actually look at. This is called feature extraction. So we have the data, and we have to filter out the specific pieces of information that you want to look at. And then we provide the model with that information, and the model will go through an iterative phase where it will train on that pieces of information and will actually fit the model to the information that it saw. And this is a very important distinction to make. When a machine learning learns something, it learns on the basis of stuff that it had seen. It does not learn on stuff that it has never seen before. Therefore, when you're hearing someone saying, I have a machine learning model, I trained it on data set A, it's now capable to find out anything and everywhere in the world, it's probably not true. Okay? Keep an eye on the details. The last point is that after the model has already learned the information, it internalized that information, the next level is to make predictions. So if I have a machine learning model that learns how to distinguish between cats and dogs, so it learns about a lot of features of cats and dogs, and now I can give it an image that it has never seen before, and it will give me a prediction, is it a cat or is it a dog? And the way that it works, it will say, okay, I've never seen this picture before, but it looks very similar to all of the pictures of cats that I've seen before, though this is probably a cat. And the prediction would be something like, this is a cat, 0.7 probability. Okay? So this is how machine learning usually works. Machine learning is not magical. I know some people think it is. It's not. It's not magical. It's not difficult. It's not complex. At least when you're starting out. And then you make a lot of fine-tuning and nuance and stuff like that. In the end, you can think about it. There used to be a show. What was the name of the incredible, the Mystery Machine, the Scooby-Doo. And in the end of each show, they would go up to the villain, and they will unmask him and show, it was you all along, you meddling kids. Whenever someone says AI or machine learning, turn off the hood, you'll see that it's linear regression. Okay? So it's not difficult, it's not complex, but in the end, it's a tool that fits some sort of problems and does not fit other types of problems. And it's a very good buzzword, just like other buzzwords that we all like blockchain and cyber and zero trust and stuff like that. So it's very good to keep it in your talks. A general rule of thumb is, it's machine learning if you see code, it's AI if you see a presentation. Keep an eye on the details. So we'll give you an example. When you write a talk and you submit to a conference, you don't say you're doing machine learning talk, you are hacking AI. You get much more acceptance rate that way. But in the end, everybody that says AI really means machine learning.
Or statistics.
Or statistics. Or linear regression. Or heuristics. In the end, it all comes down to the same thing. So it's not that we're not on board the hype train, just we have a different look from the inside. So what is machine learning good for, if I already described all the stuff that it isn't? It's very good at finding patterns. And we, as researchers trying to find patterns, it's a good tool to have in our arsenal. Because if I need to scan 1 million log lines to find some patterns, obviously I'm not going to do it manually, having it run on my screen, trying to catch this something is misformatted. I'll give it to a tool who will do grep and find it much better than myself. The same way machine learning can find patterns where us as humans can't really see those patterns. Another thing that machine learning is very good at is looking at variable A, variable B, and variable C, and say these variables correlate together in some sort of way. And if you can look at that information, sometimes you can find new links, new opportunities that you haven't thought about before. So if you feed it the right information and you find the right correlations, you can learn something new about your data set that you didn't know beforehand. And in the end, something that you can do with machine learning, it's a bit difficult to do with a bash script, you can abstract the problem, throw it at machine learning, and see if something comes out the other end. And if something does come out the other end, it means that there's some sort of structured information there that the machine learning was able to catch on to, which means that you can catch on to, which means that you found something new that you didn't know before. And this is kind of what we were going for here. We knew how to find exploitable patterns in code. We didn't know how to write programs that will find exploitable patterns in code. So we just abstracted the problem away and called it machine learning and said, look, this is something that is exploitable. I know it's exploitable. You find out why and tell me. So this is what we tried to achieve. We wanted a system that we will give it some input and it will tell us this is exploitable and why. Okay. Part of the problem is that machine learning is giving predictions based on information that it has seen in the past. So if I give it some sort of a new exploitable path that it has never seen before, it will not be really able to tell me that this is exploitable. And this is something that we kind of took into account. So, okay, there are 80% of the exploits out in the world come out of the same root causes. So if you train the machine to find these root causes, we will cover 80% of the world. And the other 20% of the world is something that we've never seen before and requires manual work, and we might miss it with this system. And you know what? That's fine. That's perfectly fine. Because if I can go over 10,000 crashes and throw away 8,000 of them because they're all the same thing, I saved a lot of time. I saved a lot of resources. And I'm very happy with that result. So what we try to do is to create this data set, test it, validate it, and to make sure that we actually have a working, I won't call it product, but at least a tool that you can use in order to better facilitate your research activities. In order to do so, we first have to teach or understand what a crash is to the machine, what it needs to focus on, and how we would go about describing those issues. So before we start describing what the machine does, we'll start with what a human does. And with that, Ezra.
So I'm going to tell you a little bit about my life. I love speaking about my life, particularly my morning life, or how I like to call it, when I arrive to the office. But actually, when I arrive to the office starts with the night before. The night before, I set up some of my fuzzers to run on certain applications and started running in the background. And I went home because I'm lazy and I need sleep. The next morning, I arrived to the office extremely early, around 11 o'clock. And I drink my first cup of coffee, because if not, I cannot continue. Afterwards, I start seeing what were the results of that fuzzing session. I open the debugger, I load into GDB the core logs from the crashes, and I start to analyze them. Based on my experience, based on what I had seen before, based on the paths that I had seen before, and the way I had analyzed crashes in the past, I classified those crashes with either a potential to be exploitable or not. And afterwards, the real fun starts, which is developing a proof of concept tool for the crash and trying to actually exploit it. This is the fun part of my day, week, year, whatever. As we have seen until now, and we had talked until now, this looks like a classical data problem, because I have multiple crashes based on experience, and I expect a result with a certain degree of probability. So if we are doing with machine learning, the machine learnings do not need sleep, nor coffee, which is probably they will start a revolution eventually. The preprocessing phase is the same thing as me opening it with a debugger and extracting the different registers and the different data that I need to perform my work. And then the machine learning analyzes the data by the same experience like I have. Like we train the model to learn from old stuff, from experience. We manage to transfer this knowledge, and it meets the same predictions. And afterwards, it will probably return to me to develop the proof of concept. We are still not on a place where the machine learning will be able to generate the payload that will generate a nice exploit proof of concept.
So in order to train our model, the first thing that we needed is something that will teach it experience, or to give it experience. And we looked about the internet, we looked about our office, we looked about our friends, and we asked everyone, do you have like a very good data set of a couple of exploitable crashes that you know what is the exploitable path in them? So you know that this program crashed, and you know that if you will use this payload, you will get a buffer overload in this address. And the answer was, yeah, I have lots of crashes. But no, I don't really know if it's exploitable or not. So the big problem was not that we weren't able to get data. We wanted good data. We wanted data that we will know that it's either really exploitable or that someone took a look at it and it's not exploitable. Because all of the other pieces of data, which is, yeah, it might be exploitable, it might not be exploitable, doesn't really help us teach the machine anything. OK. Sorry. So we searched about, we talked to people, and finally we stumbled upon DARPA's Grand Cyber Challenge. And the reason that this really came as a huge bonus for us is because they've already done all of that work for us for that competition. So I will not go into details what the DARPA Cyber Grand Challenge was. However, what they do provide is they provide 632 different exploitable crashes that come with a nice little wiki that says exactly for each and every binary what kind of exploitation technique you can use against that binary, and they already wrote the exploits. So now we have a data set where we know for each and every binary in that data set that it is exploitable, and we know how exactly it's exploitable. So now we have something that we can use to teach the machine. So we took that data set and we ran it through that open source exploitable. And the open source told us that out of that 632 cases, 607 are definitely exploitable, 12 were probably exploitable, and it didn't have an answer regarding the other 13. So this is our baseline. That means we know that all 632 are really, really exploitable, and the open source package only found 607 to be exploitable. So this is the baseline that we are going to measure ourselves against. Can we do better than that? So in order to do that, we looked at what kind of information we can use. And we have tons of information. We can look at the registers. We can look at the addresses, at the stack itself. We can look at the heap. We can look at the control flow information. We can look at a lot of different pieces of information. And after we analyzed a lot of that, we said, screw it, we don't know. We'll just take something simple, see if it works. And if it doesn't work, we'll make it more complex. But let's start small. So we started with just the regular registers, the EIX, EBX, pointers, and segment registers, stuff like that. So our first step, we take the crash dump. Then we extracted the registers from the crash dump. And we fed those registers for each crash. We fed it to the machine learning to teach it something. And we'll talk a bit about how we taught the machine. So we created a pipeline that just ran the binary. The binary crashed. We captured the crash logs, the crash dump. We analyzed the crash dump. And we took that crash dump and forked it into two different processes. The first one took it and ran it against exploitable, and the other against the machine learning under test. OK? So we can compare those results. And then we hit a problem. We hit a lot of problems. This is just the first one I'm going to describe. And maybe someone can see the problem right from this graph. This graph is just showing the value histogram, sorry, not histogram, the value spread for the ECX register. And what you can see here, that if you look at the value of the ECX register over the 632 different runs of the program, of the different programs, you see a lot of times it's a very low value. Sometimes it's a high value. And very not often it's somewhere in between. But that means is that most of the time when we are running this and we get a crash, we'll either have a very low value or a very high value. So what does low value and high value mean here? A register holds a piece of information. The ECX register usually holds either one of two types of information. Either it's a value for computation, like 1 + 1, 2 + 3. Usually it's a very low value. Or it's an address. An address is usually something which is very large, because the way of the address is structured if you translate it into an integer value. So either the ECX is holding an address, or either the ECX is holding a value. So that's kind of what you see in this graph. And these two cases are dramatically not the same. Because if I have a crash and ECX was holding an address, this is something interesting of type 1. And if we had a crash and he held only a value like 5, it's interesting, but of a wholly different degree. So we needed a method, a way to differentiate between the two cases, because when we tried to teach the machine learning model this, it just got really, really confused, because it didn't know how to differentiate them. So what did we do? So there are a couple of different techniques of how to circumvent this problem. The technique that we finally decided to go with is something called binning. Binning is to take your value space and just chop it up into blocks. You can do it uniformly or you can do it ununiformly. But in the end, we just took the easiest route. We are lazy, as Ezra mentioned. And we took the entire range and split it into 10 different blocks. And then most of our values either fell in the first block or in the last block. And very uncommonly, somewhere in the blocks in between. But once we did that, and we could teach the machine that says, OK, if you see something in the first block, this is type A. And if you see something in the high block, this is type B. It made it much easier for the machine to understand and actually analyzing the value of the ECX register in each machine. Because we don't really care about the value. We just cared about the different cases. So the first machine learning model that we tried to use, maybe a small introduction before that. Usually when people are discussing machine learning, they mean a very specific type of machine learning, and that is the neural networks. This is like the most common case. Neural networks is great, but we obviously couldn't use it. And I say obviously because it's really not obvious. So one of the things that I said you really need to mind the details is that in order to use any type of machine learning or more advanced models, you have to tell it something about the good cases, but also about the bad cases. So you have to teach it like a crash that is exploitable, but also teach it about a crash that is not exploitable. And this is a big problem because we have a big data set, well, not that big, but pretty big data set, 632 crashes that we know that they are exploitable. But we don't really have the other kind. We don't have a crash that we analyze and we know for certain that it's not exploitable. And this is also a very tough cookie because in order to validate that some crash is not exploitable, you still need to invest time and effort and resources to analyze it, to have someone sign off of it and say, no, this is not exploitable. And usually it comes with like a mild guarantee. I don't think I can exploit this. Maybe it's exploitable by someone else. So we can't really know if something is not exploitable. We know when it is exploitable because we know how to exploit it. But we are not really sure if it's not exploitable by the mere fact that we didn't find a way to exploit it. So it's not the same thing. So what we chose to do is to go into a different branch of machine learning algorithms that take a single class. A single class algorithm just says that you only know one thing about the problem. You don't have a lot of types of information about the problem. So what we do here is we know all of our data set actually fits into the same class. We know it's exploitable. Remember, we have the wiki. And now we will use these types of machine learning algorithms in order to teach it something that we already know. So the first type of algorithm is called OneClassSVM, or one-class support vector machines. And very hand-wavingly, I will explain how it works. So imagine we have these black spots and these white spots, and we are trying to find a line that will separate the two groups from one another. Okay, this is what the machine learning does. It will try to find the right equation for this line, the right parameters for the equation for this line that will give us the best separation between the white dots and the black dots. So the green one, here it's marked H1, is a very bad separation. We all see that it's a very bad separation because it doesn't really separate them. So what the machine learning algorithm will do, it will change the parameters and we'll skew it a bit. Now we have H2, the blue line. So this is a good separation because all the black points are on one side and all of the white points are on another side. But mathematically speaking, it's not the best separation that we can get because if we'll keep changing it until we have H3, this is the red line, the average distance of each spot from the line will be the smallest for the red line versus the blue line. So what I'm trying to say here, that even though The blue line is a good separation. It's not the best that we can do. So usually what we do with machine learning algorithms, we're trying to find the optimal separation between these two classes, two groups of information. So this is what we did with SVM. And just to reiterate what we know that the entire 632 points are all exploitable, but we took only 609 of them, those that exploitable, the open source, found to be exploitable, and we used this as our common base. We taught the SVM that, look, all of these points belong into the same group. Now check out the rest of the points and tell me, do they belong to that group or not? So you can imagine it like this. We took those groups, we clustered them together, and now for each new group that I'm adding, I can calculate the distance between that new group, between this new sample and the group that I had from before. And if it's close to the cluster, it's exploitable. And if it's far away from the cluster, it means that it's not exploitable. Okay? So this is what we've done. And we got pretty good results. From those 23 records that exploitable wasn't sure or didn't know about, 23 of them we found to be exploitable, and 2 more were probably exploitable. Okay, so we really outperformed the open source package. Okay, just by looking at the same pieces of data from a different perspective. Okay? And that wasn't enough. We wanted to test a couple of other algorithms to see at least the lay of the land. Can we find a better algorithm, something more robust? Again, we really wanted to increase our own trust in the model because we don't really trust it. So another model is called cosine similarity. Cosine similarity just means that we are going to measure the cosine of the distance between 2 points. So here in this graph, we have 2 points, a burger and a sandwich. Obviously, they are kind of the same class, but not really the same thing. Is burger a sandwich? I'm not sure if it translates well to English. I don't think that burger is a sandwich. And then we calculate the cosine difference between them. And if you're very, very interested, here's the formula. You don't really need it. And we looked at that model, and we used it to calculate the distance. And we got other results. And here, we got 16 more samples to be exploitable. We're still outperforming the open source package, but we are not outperforming it by much. And then we changed the model from linear cosine similarity to centroid cosine similarity. I know it sounds scary, but all it means is that instead of looking at the distance as a straight line, we are looking at it as a sphere and a spherical distance between points. So when we change that algorithm, suddenly we can cluster more points together, just by looking at it as how far away are those points on a sphere versus how far away are they in a straight line. Again, we outperformed the open source package by a significant amount. We also played with how many registers we are feeding into the machine learning to see do we really need all of those registers to get those results. And we started with 9 registers, and we got 65%, which is good. And we upped it to 15 registers. Now we got 87%. So we fed it more information that it had previously, and we got better results. Not very surprising. The last model is called XGBoost. XGBoost is something that's probably the most similar to neural networks, which people are very familiar with. And that is we took 80% of the data, we used it for training, and we kept the other 20% for test and validation. And, excuse me. And that is actually not very useful. It's useful just in one parameter. We found out that we have between 95 to 99% accuracy for this type of phone, for XGBoost. It means, sorry? Yeah, it was bullshit. So we looked at that and said, okay, we have 99% success rate for this. It just doesn't make sense. And then we looked at the data and we found out that we were pretty much lying to ourselves most of the time. Because if we looked at the data, remember we had 632 crashes. Out of them, 609 we all agreed that were exploitable. And that means if we only guessed exploitable, we will be correct 96% of the times. Which mainly means that there's no randomness involved. There's nothing to learn. If I ask my 3-year-old son to just keep saying no, 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 he will be correct some of the times. Really? So we didn't really learn anything useful. However, XGBoost does give us something else. And this is called the decision tree. And the decision tree, what it does, it takes each parameter that XGBoost is basing its decision on it and puts it into a tree structure. And that way you can visualize which parameters were more important to make decisions on XGBoost. And that gives you insight into the parameters that have the most impact in your data set. Which registers are more important than others? Which data points are more interesting to look at than others? So just to walk you through it. If you're looking at EBP, again, is EBP in bin 1? Assume that it is. Is ESI in bin 1? Assume that it is. Is ESX in bin 1? Yes, it is. Then we have 16 records that fit this filtering criteria. Out of them, 7 are exploitable, 4 are probably exploitable, and 5 are unknown. So this gives you an insight into the way that the data is structured. So let's look at it in a different way. EBP is not in bin 1, and ESP is not in bin 2. If that is true, then 571 records are exploitable. Which means that now we have a very good rule of thumb. We'll just look at the crash, and if EBP is not in bin 1 and ESP is not in bin 2, we now know it's exploitable. Success. Now we can profit. As Ezra so eloquently put it before, bullshit. This means absolutely nothing, because that's the way that the data is structured for those samples, and we use the model that needs to have input about the other completing side of the information, which is what does a non-exploitable path look like, which it never saw. It didn't know. It didn't train on any unexploitable path because we don't have that data. And that means that even though we have that decision tree, it didn't really teach us something useful. And this is something else that you have to really keep your eye on the details here. When someone gives you information statistics out of those machine learning models, statistics are great, and they really describe the way that that machine learning model was ran and trained on, but it does not give you any kind of insight what was the data that it was training on. So if you don't know what the training data was, what it was statistical properties, anything on it, looking at the results out of context, you just get that, results out of context. Just like I got a 99% success rate. It means absolutely nothing. So to conclude this, let's say, experiment or this journey that we took with machine learning is that, yes, we can take the same kind of samples and compete against exploitable, the open source package, and we can outperform the open source package. But the open source package knows how to deal with instances from the real world. Our machine learning model has no idea about the real world. It just knows those 632 samples that it saw. If we try to fit it new information, new pieces of information never saw before, will these hold true? Will this still find stuff to be exploitable when it isn't? Or when it is? We actually don't know. We don't have enough information to make those decisions. And we believe, we have at least a gut feeling that this is true, which means that if you can think about the open source package as a set of heuristics that describe a set of rules that if you follow those rules, you will know that something is exploitable or not. Machine learning does the same thing. It describes another set of rules that if you follow them, something will be exploitable or not. What we're trying to say here is that our model is probably not well trained enough to be useful in a real world scenario. But if someone wants to take it and train it, or take a different path and train it, he will still probably get very good results, probably better results than the open source package. So in order to build this yourself, you can do it. You don't need a mathematical background. You don't need a data science background, and which is a common misconception. In order to build machine learning models, you need probably to know Python. In order to write new machine learning algorithms, you probably need a PhD. It's not the same thing. So don't be afraid. Go ahead. Pick out your favorite data science package. Talk to your favorite data scientist and ask some advice. And build it. It's not that difficult. It's not that hard. It probably burns some CPU hours. And that's it. You'll have some results. You'll need experience to interpret them. but the way that we gain experience is by hacking things together and trying them out. Oh, and if you want our white paper, the white paper describes everything that we've discussed, but also gives you references and tools that we've used. I'll step aside. OK. So in conclusion, machine learning in the end is very good at finding patterns that humans are not very good at finding them. It's very good at matching pieces, different variables together and finding correlations between them. And it's very good in misleading us into interpreting the wrong results. So you have to be very careful when you do that. But if you are careful when you do that, you can get good results. I'm not dissing machine learning. I'm just saying use it with caution. In the end, we don't have enough non-exploitable crashes in order to fully train our model, which is, as we've said in the beginning, the biggest problem is getting good data. And this is the biggest problem for anyone who's playing in the data science field, which is also the reason why the biggest players are people who have access to lots of data, such as Facebook, Google, Amazon, everyone else who has access to huge amounts of data will have the best machine learning models. Imagine that it actually worked and it was open sourced and you can use it and it would fit any kind of problem in the world. What could you use this for? So we thought about 3 main use cases, out of which one was very interesting to us, but we think that it might be interesting for others. So the first one would be, imagine that you had a system that would look at a crash and tell you if it's exploitable or not, with a high degree of confidence. And that means if you hook it up into your favorite bug tracker, you can very easily talk to your developers and say, reprioritize your bugs because these bugs are exploitables and these bugs are not. And it's a new way to look at prioritization for bugs, at least from a security perspective. Because if we could fix all of those exploitable bugs first, our attack surface would be closed much faster. The second area, which was very interesting for us, is for vulnerability hunters. Take those 10,000 crashes, throw 9,900 of them in the garbage, remain 100, just look at 100. It's much better for a vulnerability hunter to focus his attention on somewhere where is a bigger expectation to actually have some yield. And the last opportunity is to actually to improve fuzzers. The basic job of a fuzzer is to find some sort of input that will crash the program. But a smart fuzzer will not just crash the program, it will crash the program and will give you those inputs that give you something that you can use those crashes for. Because if it just crashes the program and nothing happens and you can't use it for nothing, it's not an interesting crash. Okay? So, to wrap this up, even though data science has the word science in its name, it's more an art than a science. Talk to anyone with a PhD in the field, he will agree with me. And in the end, we can learn a lot and we can use a lot from other disciplines. So we had a data scientist in our team, and that helped us look at those data problems from a new perspective, from a new angle that we haven't considered before. And it actually led us into this path to find out that we can improve the way that we look at things. We can improve the way that we are doing our day-to-day jobs and save money and save time and resources. So we would like to acknowledge Dennis, who's the PhD on our team that did, on my previous team, that did this work on the machine learning side, and both Ezra and myself on the binary exploitation side of the matter. The people behind the exploitable open source package, which is amazing, and if you're in the field, you're probably already aware of it. And the people behind the Cyber Grant Challenge, which obviously, without that data set, we wouldn't be here today. So thank to all of them, and thank you. And yeah, you can. And we have time for questions. Please, don't be shy. They don't have questions. They are running away. Yeah.
Are we at a point where SOC analysts or those aspiring to be a SOC analyst should actually become data scientists?
Well, the question was, you probably all heard of them with the microphone. It's a tough question. A data scientist is usually someone who has a very deep familiarity with the algorithmic side of machine learning. When you're in a SOC, you're not interested in the performance of the algorithm, developing new algorithms. You're actually interested in applying those algorithms. So I would say someone in a SOC doesn't need to be a data scientist, but he should be a data analyst at least. And that should be at least know how to run queries against any kind of language, SQL, whatever you can imagine. It will make him a better analyst. But also understanding the way the data is structured, it will help him improve his queries, and that means he is already on the path to being a data analyst. Yeah, more questions, please. No, behind him.
Sorry.
Thank you.
Basically, because most of the techniques you've used actually do keep the interpretability of the features they found important. Is that one of the things that you actually took away from that whole process to maybe develop further techniques of detecting exploitable crashes?
Yeah, so we looked at it and we tried to find out, well, let me rephrase this and maybe answer the same question, I hope. Looking at all of the crashes that we looked at and the machine learning models that we developed, it looked like there are pieces of information, features that if we look at them, we'll have a higher probability to know if something is exploitable or not. So this is part of the reason that we did this research, because instead of looking at the entire data that we can look at a crash, if we could just focus on a specific slice of data from that crash, would make our job easier. So the shorter answer is yes, you can. The larger answer, no, it doesn't hold up in the real world. And the reason for that is that the machine learning models that we trained gave us information about the information that they saw. So they were very good at focusing your attention and with results that are relevant for these 632 test cases. But once we took that same models and put them in something new that they've never seen before, it would skew. However, if we had like 1 million test cases covering real-world use cases, we could probably have better insight and we'll get a different focus, and that focus would be probably more true for a broader sense of cases.
Let me expand a little bit in this. There's a second important thing here. In this particular kind of machine learning, we are not so concerned about misaccuracy, misrepresentation, because our objective is to find unexploitable bugs, and we have the assumption that there are multiple of them. So if we miss one of them, it's not that bad as in traditional defensive machine learning. Does it make sense?
Do you have any ideas about how to expand your data set? Or maybe crowdsourcing something from people who are vulnerability researchers, something like that?
So we have some ideas, and we actually do ask every time we give a talk like this, people, if they have information, please share it with us. The problem is that most of the people that have that information cannot share it with other people. So if we talk to like a large vendor, I don't know, Sentinel-1, Silence, Carbon Black, whoever, who have access to those data points, they can't share those data points with us, both from legal perspective, business perspective, and others. So it's floating out there. Usually you can't really touch it. It's part of the problem of getting good data. So if someone has like a very brilliant idea of how to go about that, we would love to hear it.
That's really the reason why we are sharing our methodology. You are probably smarter than us and have more resources than us. Somebody in the audience will be able to build from this and make something way better.
Yeah.
It looks like you were mainly doing memory register fuzzing. What libraries and modules were you using to do that?
What do you mean, AFL?
For the fuzzing, which libraries and modules did you use for the memory fuzzing?
Well, we were using AFL.
So maybe I'll explain for different. We didn't do specifically memory fuzzing. What we've done is use AFL to find a crash. When we found the crash, we configured the Linux backend to save the crash dump, and then we had a Python script running, analyzing the crash dump and extracting the information that we cared about. At this point, we cared about registers, but we actually had a trove of information to look at, which we didn't. We just looked at the registers because that's the decision that we've made. It's not a necessity.
So my question is this. So in the data science world, they're always talking about how much data do you need to actually create a viable model. And he talked about and you've talked about the limitations of the data set you can get. How much data do you need to get a viable model? And
it's actually a big open question, the relationship between the amount of data that you need versus the accuracy of the model that you're trying to build. So there is a graph, which I can't show because I don't have it here, but it looks like something like this. And it means it's a nonlinear graph. It means that in the beginning, when you're building your model, you need more high accuracy data and less of it. And as your accuracy increases when you're fine-tuning your model, you have more accuracy, you'll need more data. And as you will increase the amounts of data, your accuracy will drop, but the model will be more robust. So there is a cutoff point where you give it more data, you don't get much improvement in your accuracy, and you're just wasting time and resources to do that. But most of the problem is getting to that point. And if someone already has more data than that point, usually he doesn't care about the question. He just has lots of data. For everyone else, if you can get into, let's say, a 60% accurate model with a fixed amount of data, and in order to get into 70% accuracy, you have to double the amount of data, you will usually stop because getting data is very expensive.
So this might be for the room as well. There's a group, I think they're called Language Theoretic. Does that sound familiar? LangSec, yeah. So those guys. If I'm remembering right, they've done some research on classes of bugs. Basically, I'll write an input parser for random input. It'll be bad, and that's where a large class of problems come from. If you start out and build a solid finite state machine that recognizes good input and bad input and all of that. So they may have some good information on non-exploitable good parsers.
Thank you, first of all. And the second thing is that I agree, but there's a caveat to that. And that is that when we are discussing inputs to the machine, we don't necessarily mean something that gets parsed by a parser. Inputs come in various forms, and it kind of hides because it's not obvious when we say inputs. Inputs, for example, is the way that the stack is structured before you call a function. It's an input to that function. However, it's not something that's user controllable in a way. So it's not like you entered your name in text field and then a bug occurred and a crash happened. Sometimes it happens because you reordered the parameters or you gave the wrong length of a parameter or something like that, which would cause the crash, but not necessarily something that a parser even gets to look at through that exploitation path. So I fully agree that better sanitation would give better security. That is, of course. However, I'm not sure how deep bugs this kind of approach will actually find. Or stop. I agree. I'm just saying the problem is larger than that. Yeah.
Here, please. So one of my questions was, you had like this 3-stage validation thing where you were checking the contents of the pointer, the index, and then the contents of the ECX register, I believe.
Yep.
Now, are you actually checking what's in the actual region of memory to validate that it's the same data overflowing the same section of memory? Or is it that you're looking at the debug logs that you were talking about?
So the answer to that is yes and no. We are looking at the specific values in the sense that we are analyzing them to read them, but we don't care about them and we are binning them, meaning that if they are between range A and B, they're all belonging to bin 1. So we don't care about the values. The other thing is that we are not looking at the crash logs. We are actually looking at the memory dump. So we get the actual register values. So this is the information that that the model is basing its decisions on. Yeah. Yeah. Any more questions, please? Just ask between you and the happy hour.
So I don't remember the presentation I saw it in, but I think someone hypothesized that AI is better at defending as opposed to adversarial types of tasks, and you were looking at exploitables. Do you agree with that hypothesis that AI is better
I'll have to look at the formulation of that hypothesis to either agree or disagree. I would say that we have some experience with the adversarial side for machine learning. We actually gave a talk right here in this room last year about that. There are some stuff that machine learning is better at. There's some stuff that it's horrendously bad at. Adversarial analysis, for example, is something that machine learning is very bad at, just from the problem that just from the reason that the problem space is so much larger than the solution space. So there's so many other inputs that could lead into the same output for machine learning, and that means that you can easily trick machine learning to do to misclassify an input, to make the wrong decisions, etc. However, in that sense, machine learning is much better at defending, because if as a defender you can create like a whitelisting set of rules and you can teach the machine learning those rules, it would be much better than you enforcing those rules on a specific data set. However, that's not the way that it's usually applied. Maybe something in the way that some security products do pattern matching, trying to do anomaly detection, stuff like that. Machine learning is much better than humans. It's not very good. It's not the same thing.
Because we need to remember that we have multiple types. Machine learning is as good as the experience it has. And for defending, it will only be able to defend what it has, and new kind of stuff.
Just to give you like an example, give you the rule of thumb here. Someone knows how often does Facebook update its machine learning models? How often? So the answer to that they reanalyze their data and update the parameters for the models on a couple of hours cadence. So they relearn, reteach the machine learning models that they have every couple of hours based on the new data that they received from the users. And that means that they have like a moving target machine learning model. Because if they kept the same machine learning model, it would drift away from what the users are doing very, very fast, which is another problem with machine learning, which we haven't discussed here at all. And kind of answers that problem. Yeah. Thank you all. If you have any more questions, we're going to stay right here. Thank you.
Thank you.